Hello, this is Dr. Grande. Welcome to my video on how to run a regression using SPSS. I have here an SPSS data file with a couple of independent variables and a dependent variable. So first let me talk about what a regression is and what it does. What a regression allows you to do is to take a look at one or more independent variables and see how well they predict the score of one dependent variable. Typically in regression we call the independent variable a predictor variable and the dependent variable an outcome variable. So in the example I have here, which is a fictitious data set I created for videos like this, we have a dependent variable here of a score on a final exam. And we have two independent variables that we believe predict to some extent the score on this particular final exam. One is the number of minutes that the student studied for the final exam, and the other predictor is the score the student received on a practice exam. So just looking at this data initially, these are 50 students and these different observations for each, these three observations for each of the 50 students. Just looking at this initially, we don't know how well the minutes of study or the score in the practice exam predict the score in the final, if they predict the score on the final at all. And running regression will answer these questions for us. So there's a few things that you want to be aware of in terms of assumptions that you want to be aware of before you run a regression, and I'm going to show you how to check for those assumptions when I run this regression. One is the sample size. Here you can see there's two independent variables. If the dependent variable is normally distributed, the lowest number of cases or participants, or in this case students, that you would want observations for would be about 20 for each independent variable. That's really the minimum. Now there are 50 total records, so we're okay there. So 20 for each independent variable would be 40 total records, and we have 50 records. You also want to look out for what they call multicollinearity between the independent variables. Meaning, are the independent variables really capturing the same construct? Are they really measuring the same thing? So is the correlation between the independent variables high? If so, you might want to drop one of those independent variables. If they're measuring the same thing, they don't add any value or much value to the regression model. We want to screen for outliers for both the independent variables and the dependent variable, or the predictor and the predictor variables and the outcome variable. You want to see that the outcome variable is normally distributed and that there is a linear relationship between the independent variable and the dependent variable, or the predictor variables and the outcome variable. So let's move to the Analyze menu selection and select Regression and then Linear, and I'll show you how to set this up so that you can screen for those assumptions, and then I'll show you how to interpret the output in SPSS. So as you can see, this is already set up, so I'm going to clear these and show you how we do this. So we know the score on the final is our outcome variable. That's our measurement, our dependent variable. So we can drag that over to dependent variable. And we know that minutes of study and the practice exam are independent variables, so they would go here. So now we want to look through the different options that you can select for regression, and we'll start at the top and work our way down. So first we have statistics. So you want the regression coefficients, you want the estimates checked off, you want the model fit checked off, R-squared change, the descriptives, the part and partial correlations, and the collinearity diagnostics. Down here, you want the case-wise diagnostics checked off. Under the plots, and I'll again these are already populated, so I'll move these back. You want to move the ZRESSID over to Y, the ZRESID, and the ZPRED, you want to move that over to X. And down here, make sure that normal probability plot is checked off. It's not by default. Now in save, there's only one thing that I check off here, and that's cooks. All right, so that's, and I'll show you how to use that. That is viewed a little differently. It's viewed in the data editor, not in the output. But I'll show you how we use Cook's distance to determine if there's any outliers. You continue, and then we have the last dialog, which is options. And here you want to exclude the cases pairwise. So what this does, excluding the cases pairwise, what this will do is if a particular variable is used in your analysis, and for any particular record that variable is missing, SPSS will exclude that record altogether. So for example, if we're looking, let me just continue. Now it'll save this, so I'm just going to close this. So on record, say record 6, if the practice exam was not populated, there's no value here, but you did have the minutes of study, when you exclude pairwise, then that record will be dropped. Exclude cases pairwise. The difference here is if you exclude cases listwise, that will exclude the record if any of the values of any of the variables are missing, regardless of whether you use them in your analysis or not. That's a different type of exclusion. So those are all the settings we need. All right, so we have statistics. This is how this will look. And plots. And of course save is just cooks. And then the options, excluding cases pairwise. And then of course the outcome variable here independent, and the predictors here in independent. And then we run the model. Or run the regression rather. And here are the results of this regression. Now, this gives you a lot of information, so I'm going to go through and show you how to interpret this data. So we see at the onset we have some descriptives. So in the score in the final, you can see the average score was around 71. The practice, the average score was a little lower at about 62, and the average minutes of study about 173. And you can see the different standard deviations. Standard deviation for the score in the final and the practice exam, pretty close. Of course, a higher standard deviation for minutes of study. Now, it's important to recognize here is that minutes of study is collected in a different unit of analysis. It's collected in minutes, whereas the practice exam is a score in an exam, and the score in the final is a score in an exam. So now let's take a look at the correlations. So between, remember we talked about the assumptions, and we have to watch out for multicollinearity between independent variables. Right? Multicollinearity is something we do not want. So if we look at the two independent variables, two predictor variables, we have minutes of study here, minutes of study, and we have its correlation with the practice exam, which is 0.668. So the general rule is you don't want the independent variables to correlate any stronger than 0.7. So this is very close to the limit, but still in the acceptable range. Still in the acceptable range because it is below 0.7, just barely below. You also want the independent variables to correlate to the outcome variable greater than 0.3. And you can see the score in the final is the outcome variable. The practice exam correlates at 0.611, well above 0.3, and the minutes of study, extremely strong correlation of 0.826. So that meets those assumptions. So now let's continue and take a look at some of the other assumptions. So I'm only skipping around the output here. So I'm in correlations now. I'm going to skip down to coefficients. And I want to show you some of the, or a couple of the collinearity statistics and how to interpret them. So we have two. We have tolerance and variance inflation factor. And you want now what the tolerance is what it explains, what it describes is how much variability for this specific independent variable is not explained by other independent variables in the model. If it's above 0.10, then you're in good shape. Clearly it is. Variance inflation factor, you want that to be less than 10, and this is way less than 10, so no worries there. Then we look at the charts, which are here at the bottom. And what we want to do here, this is called a probability plot. Right, this is a normal probability plot. And you can see that what we want is the points to be relatively close to this line. And even though there is some deviation here, you can see some deviation up here, down here, generally we look at this and we think, okay, this does follow the line. Okay. Another way to look at this is through the scatter plot. And what you want to see in the scatter plot is the points all falling in a rectangle and no point exceeding 3 or -3 along the y or the x-axis. So you see there is a point down here that's close to the -3, but it's still pretty good. And you can see here the highest point is 2, so well within 3. Similarly, -2, there's not one point lower than that horizontally. And down here there's not a point on the x-axis that's really even near 2. So this is a good scatter plot. So really what we want is standard deviation. We want to be from -3 to 3. Now a small number of outliers is okay. It's difficult to find a data set in social sciences that doesn't have some outliers, especially if your sample size is large. So a few outliers are okay, but if you look down at this plot and there's a lot between, say, -3 and 4, or 3 and 4 up here, or going horizontally, then you might want to take a look and see if you have some rationale for dropping those records from the analysis. That can't be done arbitrarily. You have to research that a bit to see if they truly were, what caused those records to be outliers. And sometimes we find a clear cause, and sometimes we don't. We'll now take a look at the standard residual, which you can find in residual statistics in this table here, standard residual. And we kind of already know this because we've looked at the plots, but you can see that we want the standard residual to range between -3 and 3. And we know that roughly 1% will fall out of that range. As I talked about before, a small number of outliers is to be expected. But you can see here the lowest score is -2.7 and the highest is about 2. So that's another way of checking. And then I'll give you one more way of checking, and that is the Cook's distance. You remember that was an item that we selected. So you have here, you don't want any Cook's distance to be greater than 1, or again, not many. And you can see that the highest is 0.292. So examining Cook's distance, again, you can see that this is a pretty good data set in terms of the assumptions for a regression. What if the maximum value, instead of 0.292, was 1.064? All right. What you would do, and this is a little different because it falls outside the results output viewer, right? This results page, it's back in the data set. So I'm just going to move this kind of out of the way and show you that we created a new variable. We saved a new variable, and it's here at COO_1. And you can see that none of the values for this variable, this is Cook's distance, exceed 1. There's the high, 0.29210, but none of them exceed 1.0. In a situation like this, with 50 records, you can just scan through and see and find the ones that are over 1. Of course, there's none here, but if there were values over 1. But for a large sample, you'd want to sort this column to bring the high values to the top, which would be sort descending. And you can see there's the high value. So if there were a value above 1, you would see that value, or if there were multiple values above 1, you would see them here at the top. And these would be the cases then that you'd want to look at a little more carefully. So now that we have made sure that we're good for all the assumptions, we've checked the assumptions for linear regression, now we can evaluate the model. That is, we can look at the model and determine what it means. We know the assumptions are good, therefore we presume that the output is reliable and valid and useful. All right. So let's take a look at the model summary. R square, right, which is also called the coefficient of determination. What R square tells us is the amount of variance expressed as a percentage that is explained in the dependent variable by the independent variables. So how much movement in the dependent variable is explained by movement in the independent variables. Right, that's what R square is. When you're evaluating a model, when you're evaluating a regression model, you like this number to be greater than 30%, or 0.3. Our R square is almost 70%. So 70% of the movement, 70% of the variance observed in the dependent variable is explained by movement in the independent variables. That's very high. That's a very high R-square value. If you had a small sample size, and we have 50 in this example here, and the minimum would be 40, so that would be this would be relatively small sample size. We typically use the adjusted R-square because R-square overestimates for small samples. So even if we were to take this and round down, which we would normally round up, it's 67%. That's still very good, right? But normally, of course, we would round this up, so we'd say 68%. But even being very conservative and skeptical about our results, we're well above 60%, and we only need to be above 30%. So now let's take a look at the ANOVA. So the model explains, the independent variables explain a lot of the variance in the outcome variable. And now looking at the ANOVA, you might recognize some of these variables from other analysis. But you see significance, 0.000. Usually when you'd write something up in a paper, you would just say less than 0.001. So, very significant result. And you have to look at this in light of the null hypothesis, which is that the slope of this line, right, is going to be 0. That's the null hypothesis that this ANOVA is testing. So what you want to know is, can the model predict the outcome better than chance? And clearly this is statistically significant, so really no worries there. If this were greater than 0.05, then we would have to accept the null hypothesis and assume that the slope is 0 for this regression. And now let's take a look at the coefficients. So we have a couple types of output here, and it's important to understand the difference. Let's start with the standardized coefficients, which are here. The standardized coefficients do kind of what they sound like they do. They express a value that's standardized for the two independent, or however many independent variables you have. In this case, the two independent variables. So you can compare the practice exam with the minutes of study on a standardized scale. And you can see when you look at the standardized coefficients, the minutes of study explain more of the change in the dependent variable, much more than the score in the practice exam. Now the reason this is important, there's a few reasons, but one of them is that if you look at the unstandardized coefficients, these are expressed in the actual units, you'll see that the two values don't look that far apart. 0.104 and 0.157, it seems like their contribution to this model, well, relatively similar. The minutes of study, a little better predictor, but not much better. But that's not the case. These are unstandardized coefficients. You'd have to look at the standardized coefficients to know how much greater one is than the other. This puts them on the same scale. These are unstandardized, they're not on the same scale. So you may ask, if the standardized coefficients are so useful, why are the unstandardized coefficients provided? Well, that's because when you use the equation for a slope, the classic y equals mx plus b, of course this would be y equals m sub 1 x sub 1 plus m sub 2 x sub 2 plus b, because you have two independent variables. These are the numbers you plug in to determine the value, the predicted value of the outcome variable, the unstandardized coefficient. So you need these numbers to use the equation to actually make the prediction. This just gives you a better idea of their values relative to each other. So then we have the, I want to explain the partial, or the part correlation which is sometimes called semi-partial correlation, and show you how we use this. The first thing that's important to understand about the part variable is this is unsquared. This is unsquared. And what this does is it explains in variance the unique contribution of the specific variable. The unique contribution. So if you were to remove this variable from the study, this would tell you how much less variance is explained in the outcome variable. So this is the unique contribution. And as you can see, the minutes of study, even squaring this number, is an important predictor. It has an important unique contribution, whereas the practice exam is very small. All right, which brings me to the final output element that I want to take a look at, which is significance. Right? And that's here in the coefficient significance. You want to look to see if there's a significant, unique contribution to the prediction of the dependent variable. And you can see that in minutes of study, there is. Right? The p-value is less than 0.001. It's highly statistically significant. But the practice exam is far from significant. 0.331. The cutoff will be 0.05. So it is not significant. So the practice exam here is not a good predictor. Is not a good predictor of the dependent variable. However, the minutes of study by the student to study for that final exam is a very good predictor. So I hope this video on how to set up a regression and run the regression and check the assumptions and interpret the results was useful to you. As always, if you have any questions or concerns, feel free to contact me and I'll be happy to assist you.